Okay, so just imagine we are taking this periodic table and rotating it to the left. So now when we would have been looking across, we are now looking from top to bottom. So here is the 1s. Here are the 2's from 2s all the way up to 2p. Here are the 3 s's all the way up to the 3 p's, and so on. If you were to take your periodic table again and rotate it, that's what we're looking at. Okay, so we see what we expect. We see that our small atoms up here at the top have the greatest ionization energy listed here on the left-hand side. But there's also something else that we see, which is kind of weird. And those are these little baubles right here. So I want to talk to you about those. So I went ahead and wrote in the elements here. So if you have the PowerPoints with you already, you don't have those elements written in. So our second element here was beryllium, third boron, and then over here we have nitrogen at the top and oxygen at the bottom. So now let's take a look at a periodic table and see why these might have unusual ionization energies. The first one we're going to start with is boron and beryllium. So I'm going to start with our beryllium right here. So beryllium, if we were to look at the electron configuration, I would say 1s2, 2s2, and the orbital diagram would look something like so. 2 electrons in the 1s, 2 electrons on the 2s. So I went ahead and did that kind of fast. But any questions on anything there for how I did the electron configuration and the orbital diagram for beryllium? All right, so next up, we're going to look at boron. So boron is 1s2, 2s2, 2p1, and if I were to do its orbital diagram, here's 1s, 2s, and here's the 2p like so. Now, once upon a time, I told you about our irregular elements, and the problem with the irregulars is they are bouncing around from seat to seat. Oops. Here, one more time. Here we go. They bounce around from orbital to orbital, and we talked about this in class as kids in the back of the minivan switching seats. And we said that this is an unstable situation. Because just like if you're driving that minivan and the kids won't stay in the same seat, these electrons jumping back and forth are really stressful to poor boron, who's trying to get them to school. So boron is a lot more unstable than beryllium. One thing that we said way back when we were talking about irregulars is that it's much more stable to have this fully filled shell. Here, the electrons on the 1s, they are set. The electrons in the 2s, they are set, unless somebody were to give it some energy to excite them, and that means put them in a flame, put them in an electrical socket, somehow giving them some electricity, some energy, they are stuck where they are. They're not going to be moving much. Sadly, our boron doesn't have that luxury. These 3 orbitals are all the same energy, so there is nothing preventing this electron from jumping around here. And once upon a time, I told you that sometimes our D elements can promote an electron and bring it up here to stabilize, but that really wouldn't do much good here. So what boron would love to do is actually just lose an electron. So what we see is that beryllium, which is very stable, has an unusually high electron, ionization energy. So our ionization energy for beryllium is higher than we expect it to be, because what we're doing is destabilizing a stable electron configuration. Now boron, on the other hand, has this rogue electron that's bouncing around, and it is very unstable. Feels like sacrilege to write on top of the periodic table. All right. All right, so boron is unstable. So it's going to have a low ionization energy. So if someone's like, hey, do you want me to take your kid to a sleepover tonight? It is like, please, please, this electron will not sit still. Please borrow my electron. So because boron has an unstable configuration, it has that lower electron affinity, and because beryllium is stable, it's got a higher electron affinity, meaning beryllium does not want to lose an electron, and boron is more than happy to do so. And that's why we see the beryllium here higher and the boron lower than we would expect. That is why in the second row here, we don't see a nice straight line like we do for our first energy level. So any questions about the difference between beryllium and boron there? All right, so here it says stability of a half-filled or fully filled shell. So although the S and P block elements do not change their electron configuration, so I see a question coming in about irregulars. So we don't see irregulars in the S and the P's, but there are more than just the period 4 and 5. They are throughout the D and the F block. The problem with the S and the P block is they're not close enough in energy to really promote that extra electron. So for anything, we see stability associated with a half-filled or a fully filled shell. So even though the S and P elements do not change their configuration, we find that they are much more stable if they're S1 or P3, or even more stable if they're S2 and P6. But to answer Jervin's question, there are more irregulars in the D and the F block besides the ones that I talked about, yes. But those are the only ones you're responsible for. All right, so questions on anything here about how it's more stable if it has either the half-filled or the fully filled shell? Okay, so let's just go ahead and take a look at what that would look like. So here's an S. Half-filled would be 1 electron. For the P's, half-filled would look like so. So those are stable enough. These electrons can't go anywhere. They can flip. They can do a spin flip. They can go up, down, but they cannot move between the orbitals. Over here where we have 2 electrons in the S, they are locked into place. They can't even spin flip because you've already got one going up. So this other one cannot go up to match it. They won't flip at the same time. They are locked into place. Same thing for the P6. They cannot move between orbitals now, and they cannot spin flip. They are stuck. So this is by far the most stable, although the half-filled is definitely more stable than having something less than half where things can move around. All right, so let's take a quick look at, zinc and germanium. Here we have the same situation. Go back to the periodic table. All right, so here we're looking at zinc and we're looking at germanium. So zinc here has a D10. It's got a fully filled D shell. So if I was looking at zinc, I would say that it is argon, 4s2, 3d10. So it has maxed out its Ds, and so there's no possibility for those electrons to move anywhere. The gallium, on the other hand, starts off the same way. But it's got one extra pesky electron. And that electron is going to jump around between the 3p orbitals. So here we have a similar thing to what we talked about earlier. So zinc is very stable. So we say it has a high IE. So high ionization energy. It's going to take a lot of energy to remove an electron because you're destabilizing the atom. Whereas over here, this is an unstable configuration. So it's going to have a low ionization energy. And that is because it's unstable now, but if you remove one electron, then you can stabilize it. And that's why we're going to see the zinc has a very high ionization energy and the gallium an extremely low one. That's why we see these little bobbles throughout the periodic table, like so. Okay, so any questions on these ideas about the half-filled and the fully filled shells being more stable? All right, so here it's written out a little bit more. So the elements with a half-filled or fully filled shell have a higher than expected first ionization energy because it is stable and removing an electron will destabilize it. So this is what we've been talking about. And an element with a with one electron more than the fully filled or half-filled subshell has a lower than expected ionization energy. So let's look at what we're talking about here. We are talking about something like gallium, where it's got one electron too many. Essentially, it would be a stable atom if only it could get rid of that one electron in the 4p. So that's what we mean down here in the second bullet. An element with one electron more than the half-filled or fully filled subshell has a lower than expected ionization energy because if it loses that one electron, it would become half-filled or fully filled. So it would become much more stable if it could get rid of that electron. So really in chemistry, just about everything we talk about, it's about being more stable, being in a lower energy state. And if you can achieve that by removing an electron, then it's not going to take very much energy to do that. If by removing the electron you make it unstable, that's an unfavorable condition and it's going to cost you a lot of energy. Okay, so questions on anything here? All right, so still talking about ionization energy, and we talked about how there's a first ionization energy and there can be more than one. So the first ionization energy is how we form our +1 ions. It's when the first electron comes off. But the second ionization energy is when we pull off the second electron. Now here we're looking at sodium, and we know sodium doesn't normally form a 2+, but we have a lot of other ones that do. We have calcium, we have magnesium, and the truth is in the laboratory we can force an extra electron, a second electron, off of pretty much any of our atoms if we really want to. And the same rule applies to all of our atoms, whether this is something like sodium that normally doesn't want to become a 2+, or something like calcium that does. And that is your first ionization energy. The energy to remove the first electron is always going to be smaller than the energy to form the second ionization. The energy to form the 2+ ion, the second ionization energy. Sorry, I got ahead of myself a little bit there. So what I was saying is listed right down here. The first ionization energy is always less than the second ionization energy, which is always less than the third ionization energy, and so on. So the first electron you take is always going to come off easiest. Second one will be harder, and so on. So the way I like to think of it, and here's another little analogy that you're welcome to block out if you don't like the analogies, is let's say you have a bike, just got it, you're really excited about it, you chain it up outside where you live, and somebody comes and steals it. So painful for you, but the person who stole it did have to put in a little bit of energy to cut the lock. Now you get a second bike, and you're like, nobody's going to steal this bike from me. So now you maybe have 3 U-locks, some other kryptonite chains, and somebody again comes and steals the bike. But they will have to put in more energy the second time because you have it chained up better. Now let's just say, horrible situation, you lose that one too and you get a third bike. Now you have the kryptonite locks, the U-locks, you've got like a Doberman outside, and You are like vigilant, you're sitting there watching. So somebody else, again, they could steal the bike, but they're going to put a lot more energy into stealing it. That's similar to what we're talking about here. So the first electron comes off fairly easily. Once it is gone, remember, the remaining electrons feel more of the power of the nucleus. So they are coming closer into the nucleus. They feel more of that effective nuclear charge. So if something wants to steal a second one, it's going to be harder. But let's say that second electron does get stolen, it does leave. Now, the remaining electrons, again, they feel more of the power of that nucleus. They're coming in closer and closer every time an electron is removed. So that is why our first ionization energy is always the lowest. It is the easiest to steal the first electron, just like it was easiest to steal your first bike, and the second electron is harder to steal, just like your second bike would be harder to steal, and so on. So any questions about that idea that the first electron is always the easiest to get, the lowest energy, and then as you go to taking the second electron, the third, and so on, it gets harder and harder to take that electron? All right, so next up what I want to talk about is a chart that's up here. And this is a chart of ionization energies. And here is I1. This is the first electron that is going to be removed. Then here is I2, second electron that will be removed. I3 is the third. I4 is the fourth, and so on. All right, so you also see this little blue staircase here, and inside here are what we call our core electrons, which we talked about earlier. Here they're called the inner shell electrons, but we've talked about them as core electrons. The core electrons are extremely hard to remove. So once upon a time, earlier tonight, we talked about the core electrons as being electrons that are part of that noble gas core. Our noble gases are extremely stable. So when you try to take a core electron, you are disturbing a noble gas configuration. The noble gases, the rock stars of the periodic table, they are the OGs of the periodic table. You cannot mess with with those noble gases. So if you try, it costs you a massive amount of energy. So if we were to look at sodium, the first electron costs you 495 kilojoules. That's a fair chunk of change, but it is nothing compared to 4,562 kilojoules. As soon as you reach into the core, we say there is a large jump. So there's a large jump in energy anytime you try to reach into the core when you want to remove a core electron. For magnesium, 738 kilojoules to start with, and then around twice that much for the next one, 1,451. But if you want to reach into its core and steal a third electron, here is the large jump. So again, when you reach into the core, you'll see a huge jump in the electron energy here, in the ionization energy. So we could say the same thing about aluminum. So here you have 3 electrons that you can take off relatively easy from aluminum. You try to reach into its core, it'll cost you 11,577 kilojoules. That is huge. That is why we don't see a aluminum 4+ ion. And likewise, if you wanted to steal a core electron from silicon, 16,091 kilojoules. You're not going to see a 5+ ion from silicon. All right. Any questions about this idea that removing a core electron costs you quite a bit of energy? Well, okay, so question here. So does it exhaust itself after it reaches into the core? We have to supply the energy. So let's say you are in a lab and you want to remove one of those electrons. We have to supply that energy. So we're doing it through a machine, and the machines don't get tired. But in terms of nature, nature would never reach into the core. It is not favorable, not energetically favorable. It's not favorable in terms of the stability of the atom. Nature does not reach into the core. Only we do, and we want to try to prove ourselves, like, I'm so bad, I can make a sodium 2+ ion. So where that energy is coming from, again, it's from our machines. All right, so other questions? Okay. So sometimes, and you're going to see this, I believe, on the practice exam and maybe even on the homework, we ask you to figure out the charge of an atom or the number of valence electrons of an atom by just looking at these series. So I want to show you how to do that, and I think I'm going to take the aluminum series. And we can do this with any of the series. Oops. There we go. Okay, and let's say that so this is an element in the third period, so our third row, and we're going to figure out what it is. So the first thing I'm going to do is look between the first ionization energy and the second ionization energy, and what I'm going to do is divide them. And I'm going to say 1817 divided by 578, and it looks like we have increased by about, I'm just going to say about 3.1. So 1817 is about 3.1 times 578. Now I'm going to look at this right here, and I'm going to say 2745 divided by 1817, and this is increased by about 1.5. So if I take the second ionization energy and then multiply it by about 1.5, I'll arrive at the third ionization energy. Now I'm going to take the fourth ionization energy, 11,577, and I'm going to divide it by 2745 like so. And this is a jump of 4.2. So this is over 4 times as much as the previous one. So here we see that we have relatively small and then a huge jump right here. So when there's a huge jump, that's how you know you've entered the core. So what that tells us is we had 1, 2, 3 valence electrons. And if we know that we had 3 valence electrons and we are in the third period, we could then go to a periodic table. And say 1, 2, 3 valence electrons, third period, boom, we're looking at aluminum. So sometimes we give you a series of ionization energies and ask you to figure out what element it is. And so what you would do is look at the difference in those jumps. And I recommend that you do that division. In this case, I2 over I1. This gives you that 3.1. This is saying I2 is over 3 times larger than I1 was. And where you see the very large jump, that tells you you're in the core. So then you add up 1, 2, 3 ionization energies that were reasonable, that weren't a huge jump. Oh, I see your question, Jervin. Give me just a moment. So 1, 2, and 3 here. And so that tells you I have 3 valence electrons. So that's how I came up with my 3 valence electrons, and we're in the 3rd period. And there's no first period in that column. What do you mean by there's no, oh, you're right. So, yes, you are right. There is no first period here. So you could not have something that would be in the first period with 3 valence electrons. You're correct. All right, so I know this is kind of a weird one, but any questions on what we're doing here? All right, so here is sort of the second half of that table. So phosphorus on to argon. And here what we're seeing is the elements that rarely form the cations. They're more likely to form an anion, except for argon, which doesn't like to form any ions because it's noble gas. So it says a high ionization energy indicates that you are removing an electron that will destabilize, the element. Sorry about that. And we have an 8 electron rule, and this is going to apply as well to our Lewis structures. So electrons are stable when they have 8 electrons in their outer valence shell. If you remove electrons from elements that have 5, 6, 7, or 8 electrons in that outer shell, you will destabilize them. So that is why from phosphorus onto argon, it is more favorable for them to gain electrons than for them to lose electrons. They're all trying to get to a noble gas configuration, but again, if they have 5, 6, 7, or 8 electrons in their valence shell, they would prefer to gain that electron than to lose it. All right, so questions on anything here? All right, so next up is electron affinity. So this is kind of the opposite of what we were talking about. So electron affinity is a measure of how much energy is given off when an atom accepts an electron. So whenever an electron is accepted, it is exothermic. It's going to give off energy. And so you could think of it as excitement, like someone's like, hey, I brought you a present, it's an electron, and chlorine is like, yay, and it gives off all this excitement. So when we see the energy for the electron affinity, it is always negative. So this is always exothermic. Okay, so here the definition is the energy released when the neutral atom gains an electron in the gas state. So again, we define them as the gas state. Even though that's not necessarily how it's going to work in the lab, this is the definition. That definition is based on the gases. So any questions here? All right, so just to compare the two, the electron affinity is involved with gaining an electron, and energy is also always released. And it's an anion or a negative ion that's going to be produced. Whereas the ionization energy involves losing an electron, you must always add energy. I like to think of it as stealing an electron. If you're going to rip an electron away, even if it's an atom that doesn't particularly want that electron, you're still pulling it away. It still costs you energy. So energy needs to be added. A cation is produced. And I talked over here about how that's negative right here, told us it was exothermic. That is, the electron affinity is exothermic. Ionization energy is positive, therefore what would we call something with a positive energy? Instead of exothermic, it is endo. There we go. Perfect. Endo as in energy needs to enter. All right, so questions on anything here? All right, so electron affinities. So a large negative number means the neutral atom is very attracted or has a strong affinity for that extra electron. So a large negative number means it's giving off a lot of energy. So when lots of energy is given off, that means it's going to a much more stable place. That means it is very fond of that electron. That means it has a strong affinity for the electron. So a small negative number means the neutral atom is not very attracted to the extra electron. So for example, we have fluorine, and fluorine here has a negative 328. That's a pretty sizable electron affinity. Fluorine, as you know, loves to form F-. It's very fond of that electron. Lithium, on the other hand, does not particularly want an electron. It'll still give off a little bit of energy, but it's kind of like, oh, okay, you want me to take an electron? Okay, I guess I can do that. Neon is like, hell no, I'm not going to take an extra electron. All right, so the larger that negative number, the more it wants the electron. So I'm going to say more. As if that fluorine was a real living person, it is more interested in the electron. And those of you who know your electronegativities from last semester, you know fluorine is the most electronegative element. Fluorine is pulling electrons whenever it can, so it is extremely interested in getting that electron. So any questions on anything here? All right, so here's a table of electron affinities, and I want to take a look at it. First off, our noble gases. They are pretty close to zero. So they do not have any interest in taking in an extra electron, but you already knew that. You knew noble gases are stable and don't want electrons. So here, if we look at our first column, these are pretty low numbers. So they will accept an electron if they have to, but they are not very interested in it. Next out, I want to point out the second column. These are our alkaline earth metals. And once upon a time, we said that these were S2s, which means they are stable. They have a full S shell. They have no P's. They do not have any movement around of those electrons. Those electrons are nice, stable, packed in there. So if you were to give them an extra electron, now they have that temperamental child who is hopping around, maybe even deciding to do a little backflip. See if I can flip it. There we go. Maybe even doing a backflip, blah, blah, blah. So it is moving around, and beryllium, magnesium, calcium, and strontium are like, oh, why did you give me this extra electron? I can't handle this. So they have no interest in taking in the extra electron. That is why they're so close to zero. Now, what you find in calcium and strontium is there's a very small electron affinity here. That tiny electron affinity is just saying that they're a little bit better able to accommodate it. And the reason is because they are very large elements. Their electrons sit very far from the nucleus. So if they have this pesky little electron that's bouncing around, and it's bouncing, having a good time, it is easier for them to handle it if that electron is sitting far from the nucleus. And so that's why we're going to see that these elements down at the bottom are a little bit more willing to take that electron in. They're still not very willing to. Like -2 is nothing, -5 is nothing, but they're more willing than beryllium and magnesium. And again, it's because that electron is so far from the nucleus. So any questions on that about our alkaline earth metals, about why they don't particularly want an extra electron? All right, so then what we see is a very general trend going up and to the right for increased electron affinity. But it is a very general trend because you have a lot of columns here that are bucking that trend. For example, the noble gases are not participating. We have the alkaline earth metals that are like, We even have this nitrogen right here that is like, what are you thinking? Why would you give me an extra electron? So let's talk about what's going on with that nitrogen. So nitrogen would have an S2P3. So here, this is a pretty stable configuration. If you gave it an extra electron, and let's make this extra electron purple, I could put it there. Let's see if I can grab it and move it. Okay, could have put it here, or here, or here, and it's going to bounce all around. So nitrogen has no interest in this extra electron. Now it's true that all of the elements in this column have a similar situation, but just like we talked about for our alkaline earth metals, as you get further down in the periodic table, they're better able to accommodate that pesky electron that keeps bouncing around because it's going to be sitting further from the nucleus. So nitrogen, no how, no way, can accommodate it because it's too close to the nucleus. It can't handle it bouncing around. But if you think of nitrogen as driving a minivan and antimony at the bottom driving a school bus, if the electron that's bouncing around is in the back of a school bus, it's a little easier to handle than if it's right behind you in the minivan. All right, so nitrogen has no interest in that extra electron either. So that's why I said it's a very general trend here for our electron affinity. There's one other kind of crazy element I want to talk to you about, and that is fluorine. So I mentioned before, fluorine is our most electronegative element. It is the element that wants electrons more than any other. If it's in a chemical bond, it's going to start pulling to itself more than any other. However, it doesn't give off as much energy as, say, chlorine below it. And so there's actually a reason for that. And the reason has to do with fluorine's size. So fluorine is very tiny. And it's tiny because it really loves those electrons and it's pulling them in tight. But because they're in so tight, there's something called an electron-electron repulsion. So the more electrons you pack in a very small element, they start getting too close together. And so those electrons are all negatively charged. And again, they get too close to each other, and that repulsion that's generated makes it higher in energy. So fluorine is actually better off being in a covalent bond where it can pull electrons than actually taking the full charge. Chlorine does a better job at taking the full charge. And again, it's just because it's so tiny and because that fluorine really doesn't have enough room for that extra electron. Now, it can take it. We know there's lots of fluoride around. There's fluoride in your toothpaste, fluoride in your water. But compared to chlorine, fluoride cannot accommodate that electron as well. And that's why it actually has a slightly smaller electron affinity. All right, so again, just one more time, it's a very rough trend for the electron affinities with lots of things that violate those rules. So that's why I didn't put the arrows on there originally, and I just kind of wrote them here in highlight. So remember, just very approximate for those arrows this time. All right. Questions on anything else here? Or anything at all here? All right, so I feel like I've been talking at you all class. You haven't had a chance to, do some good old-fashioned calculations. So I think I'm going to talk to you about one last thing, and that is the metallic character. And then I think we're going to break lecture here, and then next class I might use a little bit of your lab period for lecture. But I said I'm not going to keep you that extra hour this time because I've been talking at you so much. I don't know if you're still even awake out there. Okay, so let's talk briefly about metallic character. So how do we use the numbers in the chart? Okay, so we're going to get to that in the next chapter. So in the next chapter, we're going to do something called lattice energy, and that's where we're going to use these numbers, and we're also going to be using these numbers right here. So we'll bring everything together next chapter. Good question. All right, so next up I want to talk about metallic character. So normally if you were asked to describe something that's metal, you'd say, hey, it's shiny, which is something we call luster. It has high luster. It might be dense, which we talked about at the beginning of the semester. It feels heavy. So those are things that we normally think of for metallic character. But in chemistry, we actually have a different definition. And here we say that the more metallic the element is, the more easily it will give up its electrons. So it's kind of a weird definition. The idea of something that's metallic is something that is very generous. It's giving its electrons very easily. And so here I've related it to size. So up in the upper right-hand corner, you know that those are your nonmetals. They are not metallic at all. And down here near real big, these are extremely metallic. So my arrows going up and to the right go towards a decreasing metallic character. And they do follow along with the size. So if you have something large, like RB, real big, so real big or rubidium, it's very large because the nucleus is not controlling those electrons very well. It's letting them wander. So because it is large, because those electrons are sitting so far from the nucleus, they can be donated very easily. Or if you want to think of it as another atom can come along and steal them very easily. Now, we already talked about fluorine. You know that fluorine hangs on to its electrons very, very tightly, and it has zero interest in donating an electron. In fact, if you try to take it, we already talked about how it's going to take a piece of your ear with it. So our large atoms are the ones that are metallic, and our definition here of metallic is that they can donate their electrons more easily because the electrons are further from the nucleus. And our small atoms are not metallic because they cannot give up those electrons very easily because they're very attracted to the nucleus. So strong Z-effective, effective nuclear charge that's keeping those electrons in tight, it makes them small and it makes them non-metallic. So the stronger the effective nuclear charge, the less metallic it is, because you need to have a very free-living hippie parent to allow the electrons to wander far enough that they can be donated easily. So again, the large atoms are going to be more metallic because they can give off an electron easier. Small atoms that hold those electrons tightly, they are not metallic because they can't give away those electrons very easily. So I know it's kind of an unusual definition for metal because we do think of it as something that can conduct electricity, something that's very shiny, something that's very dense, but this is our chemistry definition here. So any questions on anything here for metallic character? All right, so next up, here we have just a couple quick practice problems. So let's do the first one together. So here we have sodium and we have aluminum. So we want to know which one has less metallic character, and there's a note here that the smaller the atom, the less metallic character it has. So which one is less metallic, sodium or aluminum? Excellent. So I see a lot of aluminum. It's good to know people are awake out there. All right. So let's actually do the second one together as well. We have rubidium, cesium, and tin. So here is our rubidium. And did cesium fall off our chart? Let's see. Here is tin, and let's see, where did our cesium go? I believe cesium fell off the chart. Hold on one sec. Yeah. Sorry about that. It fell off our chart here. Cesium should have been right here. Okay, so these are the three elements we're looking at, cesium, rubidium, and tin. We want to know which one will have the least metallic character. It looks like we already got a vote for tin, so go ahead and take a minute and then type in which one you think. Got a couple votes for tin coming through. All right, so it is indeed tin. Oops. So between cesium and rubidium, it is rubidium that is smaller, therefore rubidium that is less metallic. And between rubidium and tin, it is tin that is smaller and less metallic. So any questions on anything here?